Your service is falling over, and the alerts will not shut up. And now, sitting in front of you is the most classic multiple-choice question in engineering history. Buy one bigger machine or buy more cheap machines? Last time we trained our order of magnitude instincts and did the math showing one machine can't carry the load. Today, we pick that question right back up. Hiding inside this one choice are the first principles of nearly every distributed system. And as usual, no armchair talk today. I ran a real round of load tests on this very laptop. First, I crushed one machine straight into the wall to see what that wall actually looks like. Then I added machines one at a time to watch when the speedup stays a straight line and when it bends over. Every number came out of a live run. First, 2 terms we need to get straight. You run a restaurant and the line is out the door. 2 ways to go. Way 1, get a bigger kitchen. More burners, hotter flames. That's vertical scaling. In proper jargon, scale up. Still one machine, just a beefier one. Way 2, open another location next door. That's horizontal scaling. Scale out. The machines stay cheap. You win with quantity. Vertical's charm is that it's painless. Not one line of code changes. Swap the machine today, and it's live tomorrow. The downsides come in a pair. Price grows super linearly. 2 times the performance often costs 4 times the price. And there's a ceiling. A single machine 100 times bigger simply does not exist. Horizontal's charm is that in theory, there's no ceiling. The downside is. Your system has to be redesigned for many machines. That's a tax, and we'll go deep on it later. And while we're here, 2 more pairs of terms, or this conversation can't move forward. Pair 1. Slow even for a single user, that's a performance problem. Fast for one person, slow when the crowd shows up, that's a scalability problem. The prescriptions are completely different. Pair 2. How long one request waits, that's latency. How many requests get handled per second, that's throughput. And you're about to see it in the live numbers. These 2 aren't just different things, they regularly fight each other. The naive idea goes like this. Not enough CPU? Swap in a faster CPU. Done. 30 years ago, that reasoning was correct. Back then, single-core performance doubled every 18 months. You slept, and your machine got faster. Not anymore. Single-core performance now creeps up a few % a year, like squeezing toothpaste. What the vendors hand you instead is more cores. But more cores does not equal a faster program. Your program has to know how to use many cores at once. That's already horizontal scaling thinking. It just happens to live inside one machine. So I built one deliberate trick into today's load test. I shrank one machine down into one process. Each process is locked to one core, and every request burns a little over 4 milliseconds of pure computation. That way, the speedup curve, the wall, the ceiling, every bit of it can be staged live on this laptop. The logic is identical to a real data center. We just swapped machines for processes. Round 1. One machine, and the concurrency goes up. Concurrency 1. 232 requests per second at 4.3 milliseconds of latency. Perfectly healthy. That's what this thing is capable of. One core divided by 4.3 milliseconds puts the theoretical ceiling around 230, and the measurement rides right on top of the theory. Then I raised concurrency to 2 to 4, all the way up to 32. Guess how much the throughput grew?
Almost none. Concurrency 2 reads 252. Concurrency 32 still reads 258. 16 times the pressure buys 2% more throughput. But the latency. The median climbs from 4.3 milliseconds to 87. The 99th percentile blows up from 4.7 milliseconds to 1,392.3 milliseconds. 1.4 seconds.
That is what the wall looks like. Commit it to memory. Throughput doesn't move an inch. Latency takes off exponentially. Once the machine is saturated, extra requests buy you no throughput at all. Everything they buy is queuing. This is the live-action version of what we said last time. Push utilization past 80%, and latency takes off. When your service crawls, Most of the time, it hasn't gotten slower. The queue has gotten longer. All right, wall thoroughly hit. On to road number 2. Add machines. The client round-robins requests across multiple instances. That round-robin is load balancing at its most primitive. Real load balancers get their own teardown a couple episodes from now. Now look at this staircase. 1 machine, 257 per second. 2 machines, 516. Exactly double. 4 machines, 1020. Exactly 4 times. And latency held around 30 milliseconds the entire way, rock steady. This is horizontal scaling at its most seductive. Add 1, get 1. Linear.
Above that, it stops being clean. 8 machines lands at 7.6 times. The missing 0.4 is the tax of fan-out and system overhead. And 12 machines? Only 8.9 times. The speedup grew a mere 17%, while the 99th percentile latency blew up from 33 milliseconds to 257.
Why? Because this laptop only has 8 performance cores. The first 8 instances get 1 core each. From the 9th on, they're fighting over somebody else's core, and the 4 efficiency cores left over are just born slow. That's the vertical ceiling, measured live and slapped right in your face. The multiplier one machine can give you is used up. To go any higher, it has to be an actual second machine. And that's exactly what horizontal scaling really means. So stack the 2 load tests together, and you get the complete answer to today's question. A single machine has a wall, and behind that wall, it's all queuing. Adding machines buys throughput linearly, right up until the machine itself is sold out. Sounds gorgeous. Just add machines and call it a day. No. Horizontal scaling collects 3 taxes, and you can't dodge a single one. Tax 1, the state tax. A user logs in on machine A. The session sits in A's memory. The next request lands on machine B. The login is gone. As long as state is welded into one particular machine, that machine can't be replaced, and you can't add machines. The prescription is going stateless. Sessions go into read as, files go into object storage, and any machine can answer any request. That's the price of admission for horizontal scaling. Tax 2, the serial tax. Textbook name, Amdahl's Law. Somewhere in your system, there's always a chunk of work that cannot be parallelized. Grabbing the same lock, writing to the same primary database, merging the same final result. The ceiling on your speedup equals 1 divided by the serial fraction. Even at just 5% serial, 10,000 machines can give you at most 20 times. Your ceiling isn't set by the machine count. It's set by the most serial stretch of your system.
Tax 3, the complexity tax. Straight from the primer. Horizontal scaling introduces complexity. Servers have to be clonable. The load balancer itself can become a single point of failure and a bottleneck. And once you run many machines, some machine is always down becomes everyday life. 1 machine's failure is an incident. 100 machines' failure is statistics.
The failure path deserves the full story too. 1 machine behind the load balancer dies. The health check pulls it out, and its traffic spreads across the survivors. Sounds lovely. But pull 1 machine out, and every remaining machine's load jumps at once. If they were already running at 80% utilization, that one moment tips the whole fleet into overload, walls hit in a chain reaction. So capacity planning for horizontal scaling always keeps headroom by 1 rule. Lose a machine and keep living. Our regular segment. How is AI going to shake this up? This one is extra fun because the GPU world is rerunning everything we just covered at eye-watering prices. The vertical route. Single cards keep getting beefier. 80 gigabytes of GPU memory, then 141, then 192. Bandwidth piled from 3.35 terabytes per second up to 8. But last time we did the math. A 70 billion parameter model is 140 gigabytes in weights alone. 1 card still can't hold it, and models are growing faster than the cards are. So the AI world was forced onto the horizontal path from day 1. Tensor parallelism slices each layer sideways across many cards. Pipeline parallelism cuts the stack vertically, layer by layer. Data parallelism copies the entire model several times over. From the day the model stops fitting on one card, horizontal scaling is not an option. It's mandatory. And Amdahl's law applies word for word. The communication and synchronization between cards is exactly that serial chunk. That's why a 10,000 card cluster never gets 10,000 times the effective compute. And it's why NVIDIA isn't just selling you cards, it's selling the network between the cards. Let's walk the 4 questions. 1. What does AI actually do here? Capacity planning as a craft is being handed over to predictive autoscaling. Old-school reactive autoscaling adds machines only after a threshold trips, half a beat late. You stall first, then you scale. Predictive autoscaling has a model learn your traffic cycles, so capacity is already in place before the peak shows up. 2. What does it replace? What goes away is the human who stares at dashboards and eyeballs a capacity number. 3. What changes? Capacity goes from guessing one comfortably big number to a curve that follows the forecast. Idle machines turn directly into money back on the bill. 4. What shifts? The engineer's job moves from tuning thresholds to backstopping the forecast. The fallback scaling rule has to stay, because one day the forecast will miss. And on that day, you're back on the hard skills from today. And let's be upfront about where AI can't help. Bigger machines or more machines? How much money peak capacity deserves? Whether that serial chunk is worth a refactor? Those are trade-offs and business judgment. A model can't hand them to you. You make the call. Before we wrap, the traps. I stepped into 3 in a row, myself running this load test, and they're all left in the episode for you. Trap 1. My server started out speaking HTTP 1.0, which hangs up after every single response. The second concurrency ramped up. Every client was reconnecting like crazy. The backlog blew out, and connection refused errors reigned everywhere. The load test wasn't testing my business logic at all. It was testing the connection handling I had misconfigured. Trap 2. After switching to keep alive, I forgot to send content length. The response arrived, but the client couldn't tell if it was finished. Every request sat waiting out the timeout, and throughput went straight to 0. Trap 3. My load test client had no timeouts set. One dead connection hung the entire bench, frozen at 0 CPU, just staring into space. 3 traps, 1 pattern. Distributed bugs mostly live in the unglamorous seams, connections, and protocols. Then come the methodology traps. 1. Don't go horizontal too early. If one machine honestly still covers you, and you're already rolling out shards and clusters, you're paying the distributed systems tax in real money to buy yourself complexity. Scale vertically until the price-performance knee, then go horizontal. Even the primer signs off on that order. 2. Load tests lie. My load test client is a program too, and it can become the bottleneck itself. Whatever wall you measure, first confirm whose wall it is, the servers or the testing tools. 3. Don't pass off processes as machines when you brag. Today's demo is a teaching model. A real data center adds network latency, racks, switches. Those get their spotlight when we tear into the traffic front door a couple episodes from now. 3 sentences to take home. Behind a single machine's wall, it's all queuing. And throughput and latency need to be read separately. Horizontal scaling buys you throughput linearly as long as you stay stateless, but it charges 3 taxes: state, serial, and complexity. Go vertical until the price-performance knee, then go horizontal. And from day 1, never weld state into a machine. Homework, same as always. Both scripts are in the description. A few dozen lines, 0 dependencies. Run them on your own machine, count how many real cores you have, and watch where the speedup bends. That bend is your machine's wall. Once you have lots of machines, the next problem walks right in. How do multiple machines keep their data consistent? If one machine dies, does the answer still count? That's the famous pick 2 out of 3 problem. Key IP. Next episode, we tear it wide open. See you next time.